imagine you're sitting down to build an app, right? But instead of writing arcane symbols or, standard code, you write verses and stanzas.
Right, like an actual poem.
Yeah, exactly. A legally binding contract, but it's airtight, deterministic, mathematically provable, and written entirely in free verse English.
It sounds kind of impossible, honestly.
It really does.
Yeah.
Because, if you swap out a standard operational word, say fold, for a poetic alias like weave, or you use chorus instead of fork, the contract doesn't break.
No, it doesn't break at all.
In fact, it compiles and executes perfectly at over 23,000 times a second.
Which is just staggering when you think about it.
Totally. You aren't just writing software anymore. You're writing literature that the machine inherently understands how to execute at the bare metal level. So today, we're doing a deep dive into the V0.9 documentation for Gnot.
Gnot, yeah. An open source topology script language.
Right. And our mission today is to figure out exactly how this language pulls off what feels like a complete paradox. Like balancing this highly expressive, plain English poetry profile at the authoring edge, but with a mathematically deterministic core that dictates, well, everything. From temporal state manipulation all the way up to multi-server application deployments.
Yeah, it fundamentally challenges the traditional trade-offs we're used to in compiler design.
Yeah.
I mean, usually you have to choose between developer ergonomics, making the code read well for humans, and execution strictness.
Like choosing between Python and Rust, basically.
Exactly. Think about a dynamic language versus a strongly typed systems language, but not just refuses to make that compromise. It uses this highly constrained, really brilliantly engineered architecture to ensure that the poetry the human writes maps flawlessly to a rigid intermediate representation that the machine actually requires.
And the mechanism they use to achieve this, the documentation, calls it a lean-style split, which I find fascinating. So let's dig into the architecture of that. Because on the surface, allowing a developer to use all these conversational aliases sounds like an absolute nightmare for the lexer and the parser.
Oh, totally. A standard parser would choke on it.
Right, because say I'm writing a high concurrency app and I want to fan out a process. The canonical term in Gnot's minimal kernel is fork. But the poetry profile allows me to use the word chorus. And if I want to terminate a branch, the kernel uses vent, but the poetry uses hush. So how is the language architected so that this doesn't introduce just massive overhead or ambiguity into the system?
Well, the lean style split essentially isolates the human experience from the machine execution completely.
Yeah.
So at the absolute bottom, you have a minimal kernel surface.
Okay.
This is your bedrock logic, the absolute basics. And then above that is the sugar elaboration layer.
The poetry part.
Right. And the bridge between them is this canonical deterministic normal form. The foundational invariant of the absolute rule is that poetic sugar is always optional and never ever semantic.
Meaning the underlying abstract syntax tree, the AST, literally doesn't even know the word chorus exists.
Precisely. The goal of that authoring edge is to provide low duplication, single concept identifiers. But here's the critical optimization. The compiler strips all of that poetic sugar away in exactly one pass during normalization.
Wow, just one pass.
Just one. It does not drag those aliases down into the execution phase. It maps chorus to fork, weave to fold, and jewel to race, and it's done.
Okay, wait, let me push back on that implementation a bit. Because if the sugar elaboration layer is allowing all these different aliases at the authoring edge, for instance, mapping app contract actions so that mutate becomes make, or query becomes learn, and subscribe becomes listen, doesn't that require the compiler to hold this massive lookup table in memory?
It sounds like it should, yeah.
Right, doesn't the constant token resolution bottleneck the initial parsing phase? I mean, why not just force the developer to write query and be done with it?
That is the classic systems engineering argument against syntactic sugar, right? But Gnot solves it through zero-cost abstractions during the lexical analysis phase. The parser, which we'll discuss in detail later, but it's written in Rust, it resolves these aliases at the token stream level before the AST is even fully constructed.
So it's like an instantaneous translation.
Exactly. It's an instantaneous mapping. And the reason they go through all this effort is to drastically lower the cognitive load on the human reader. Because look, in enterprise environments, code is read maybe 10 times more often than it is written.
Yeah, that's so true. You spend way more time trying to figure out what the last person did.
Exactly. So when an auditor or a systems architect looks at a complex concurrent block, seeing the word dual instantly communicates intent. It means two discrete processes are racing, and the first to return wins.
Ah, I see.
And weave visually implies aggregating multiple discrete threads of data into a single payload. It communicates intent through this mechanical metaphor.
That makes a lot of sense. It's about optimizing for human-to-human communication, but without sacrificing the machine readability. And Gnot takes this aesthetic very seriously. The documentation explicitly states that legacy punctuation-only shorthand is forbidden in the poetry profile.
That's right. No shortcuts.
You can't just throw an arrow operator like a dash and a greater than sign in there to replace a qualifier word. It physically forces you to write out the English.
It does. It enforces a very clean, text-heavy visual landscape. Semicolons are optional, restricted mostly to compacting one-line split arms where visual density is actually helpful.
Okay.
And for multi-line literals, instead of navigating complex, quote, escaping, which is always a headache, you just use strict fence backticks.
So it's forcing a really specific visual aesthetic, almost like a brilliant simultaneous translator who takes your casual conversational English and instantly writes an airtight legal document. But look, if you give developers the freedom to write in plain English poetry, to use words like listen, learn, and make, the immediate danger is that they will treat the code like literal free verse.
Oh, absolutely. That's the risk.
Right, because in standard human languages, we can structure sentences in dozens of ways and still convey the exact same meaning. I can say, to the database, the server sent the payload, or the server sent the payload to the database.
Both are valid English.
Exactly. So if the compiler is instantly mapping these poetic tokens into a rigid kernel, how on earth does it handle the inherently chaotic geometry of human grammar?
Well, the short answer is it doesn't handle chaotic grammar. It outlaws it completely.
Oh, really?
Yeah. And this is the necessary counterweight to the linguistic freedom of those aliases we just talked about. Gnot enforces an absolutely rigid sentence structure called the Sphyghian canon.
The Sphyghian canon.
Right. So you have complete freedom in the vocabulary you use to describe the logic, but zero freedom in the grammatical sequence of that logic.
Zero freedom. Wow. Okay, so it dictates a mandatory canonical qualifier order for every single executable line in the language. And the rules are unyielding, right? Like active tense only and exactly one verb per line.
Exactly one verb. And to help developers internalize this strict geometry, the documentation actually provides a memory lock phrase. It goes, Wenceslas's wheat field to Warsaw. Why? With vodka by war's destruction.
I mean, it sounds like a line from a highly depressing geopolitical thriller.
It really does.
But if we break this mnemonic down, it maps flawlessly to the 11 allowed syntax lanes in the Gnot compiler. Let's trace how a piece of logic actually moves through these 11 lanes, because I feel like this is where the language's unique approach to intermediate representation really crystallizes.
Let's do it. So the first lane maps to Wenceslas's. This is the who lane. The protagonist or the actor initiating the operation.
Okay, so for example, an authenticated user.
Exactly. The user is the who. The next lane is wheat, which maps to what. This is the payload or the subject being acted upon.
Like a JSON payload containing a status update or something?
Perfect. Then we have field mapping to the from lane. This establishes the provenance, the origin endpoint.
Got it.
Next is to, which obviously represents the destination lane.
So just to recap the first four, we have the user, the who, sending a status update, the what from the client application, the from to the primary ingestion server, the to.
All right, we've built the core action, but there's 7 more lanes.
Right, the sentence keeps going.
And they add all the necessary operational context. So Warsaw maps to where, which is the locus or scene of the operation. It's a dual read as Warsaw, which is kind of clever.
Yeah.
Then why maps to the Y lane. This is a dedicated space for explicit rationale or purpose tagging.
That's really interesting because usually rationale is just hidden in a code comment that the compiler completely ignores, right? But here the Y is structurally integrated into the syntax line itself.
Exactly.
What?
Because in a deterministic system, the rationale can sometimes inform the audit trail. You want it in the code.
Okay.
Next, with maps to the with lane, carrying extra contextual data.
Okay.
Vodka maps to via, dictating the path or the medium, like, say, a specific WebSocket protocol.
Sure.
By represents the method or metric lane.
And then we get to the temporal constraints, which are incredibly important in Gnot. Wars maps to the when lane, the trigger, or the condition.
Hmm.
And finally, destruction maps to during, the duration, or window lane.
Right, so if you utilize all 11 of these qualifiers on a single line of execution, they absolutely must appear in this exact chronological order: who, what, from, to, where, why, with, via, by, when, doing. You can omit the optional ones, sure, but you cannot invert them.
Okay, let's look at the mechanical implications of this. From a compiler design perspective, why force this? If the Rust lexer is powerful enough to strip away aliases in a single pass, why isn't it powerful enough to resolve a why clause that appears before a where clause?
That's a fair question.
I mean, modern AST parsers handle non-linear clause resolution all the time. So why is not so draconian about this exact geometry? Doesn't forcing me into this exact 11-step sequence kind of stifle creativity?
Well, it comes down to establishing what the documentation calls replay-safe guardrails. Yes, a modern parser can totally resolve nonlinear grammar, but allowing nonlinear grammar introduces ambiguity when a deterministic system needs to rebuild a state exactly as it occurred. But fixing the geometry of the sentence, the compiler generates a perfectly uniform AST. There are no edge cases where a trailing clause modifies an earlier state unexpectedly.
So it's really about eliminating the possibility of parsing collisions during complex state evaluations.
Exactly. Look at how Gnot handles terminal clauses within this scaffolding. A terminal clause is anything that attempts to exit a flow early, like a yield that returns a payload, or event that hushes a branch.
Right.
The strict rule is that any non-final terminal clause must be guarded by a when condition.
Meaning you can't just have an implicit fall through. Like if you are exiting the block before the natural end, you have to explicitly declare when that exit is legally allowed to happen.
And because when lane is rigidly fixed near the very end of the Svichkin canon, the compiler knows exactly where to look for that condition. It doesn't have to scan the entire block to figure out under what conditions the yield triggers. It's mathematically predictable.
Which makes it so much safer. And the strictness applies to destructive operations too, right? Like you can use a wildcard, the underscore, to discard a bound component during pattern matching. But it is explicitly illegal to use the wildcard in the who lane. You cannot have an anonymous void as an active subject.
Which makes perfect sense in a system designed for perfect audibility. The wildcard is a discard token. It cannot initiate an action. These guardrails ensure that when the poetic sugar is stripped away, what remains is a mathematically provable series of state transitions.
Which bridges us perfectly to the concept of time. You pointed out that the last two lanes of the canon are when and during. And the documentation makes it very clear that time is not just a metadata tag appended to a log file.
No, not at all.
Time is a physical, traversable dimension within the language's native syntax.
Yeah, Gnot handles time through temporal cursors, specifically utilizing the tilde character.
Right, the little squiggly line. So just a plain tilde represents the current admitted cursor, the very latest time point in the application state. But the syntax allows you to write tilde n, which represents a historical offset. You are natively referencing a state n steps before the current cursor.
Exactly.
Conceptually, it's just fascinating. It's like having a native undo button built into the fabric of reality, or like a video game save state. Because it's really rare for a language to natively understand stepping back n frames without building out complex custom logging systems.
It is rare. And it leverages an architecture that's similar to event sourcing, but combined with strict immutability. So in Gnot, values are single assignment within a specific flow. When a verb executes, it derives a new value. It absolutely never mutates a prior binding.
Wait, so it never overwrites a variable?
Never.
So it's an append-only progression. State isn't like a chalkboard that gets erased and rewritten. It's a ledger where new lines are continuously added.
Exactly. And this leads to the foundational theorem of Gnosis determinism that the whole language relies on. Same admitted inputs plus same cursor plus same config equals the exact same outputs always.
Always. Wow.
Because you never destroy old data via mutation. Evaluating a tilde 5 isn't a complex database query. It's just pointing the compiler to a known, immutable node on the execution tree.
Right. It's like checking out an older commit in a Git repository's Merkle tree. The history is mathematically linked. But wait, if the system is perfectly deterministic, how do you handle side effects? Because what if an application needs to generate a cryptographic key, which requires randomness, or it needs to read from a real-time external sensor? Doesn't injecting non-determinism just break this append-only ledger?
This is where Gnot's architecture is particularly elegant, I think. It introduces what they call quantum lanes,
Quantum lanes.
Okay.
operations that introduce non-deterministic states, like the superpose command, are permitted, but they require an explicit deterministic seed to be injected at the syntax level.
So you can have a random number generator, but you have to prove to the compiler how that randomness is initialized.
Yes. If you attempt to compile a script with an unseeded non-deterministic source, the gnarly parser will throw a hard error and fail the build entirely.
It just stops you.
It physically prevents you from deploying a state that cannot be historically replayed. So when you replay a flow to evaluate a historical cursor, the replay must specify the deterministic mode so it can exactly recreate the randomness of that specific moment.
That is wild. And what happens if you try to evaluate a cursor that no longer exists? Say I query ~1000, but the system has pruned its history to save memory and only retains the last 500 steps. In C++, psi, that's undefined behavior, right? Like a seg fault waiting to happen.
Yeah, a total crash.
Right.
But in Gnot, an underflow attempting to read beyond retained history triggers an explicit tagged error at the compiler level. The system is entirely aware of its own memory boundaries. This append-only progression is critical for stateful substrates, what the documentation calls knot graph tips.
Right.
If you're building decentralized applications or consensus protocols, you must be able to mathematically prove the state at the current tilde by deriving it sequentially from known historical nodes.
It effectively bakes the security of a blockchain ledger directly into the compiler's syntax tree. That is incredible. Now, to support this level of complex state tracking, where every payload has a specific origin, destination, actor, and temporal state, standard variable naming conventions become pretty inadequate, don't they?
Oh, totally.
Because if I just name a variable target data, the compiler doesn't inherently know if that data is the actor, the destination, or the method. It just sees a string.
Which is why Gnot integrates the cross-linguistic case atlas.
And I think this is a profound shift in how we think about passing data. Instead of relying on human conventions for naming variables, Gnot uses a with cases syntax block to assign machines stable role semantics.
Right, and they actually borrowed the structural concepts from case-rich human languages like Russian, Finnish, and Basque.
Which is such a unique approach for a programming language.
It really is, because in English, we rely almost entirely on word order. Like, the server queried the database means something totally different from the database queried the server.
Yeah.
But in case-inflected languages, the suffix of the noun itself dictates its role, regardless of where it sits in the sentence.
Exactly. And Gnot maps these concepts into specific assignable cases for data payloads. So for core alignment, you have erg for the ergative case, abs for absolutive, nom for nominative, and ac for accusative. Okay, and it provides cases for possession and recipient roles too, like gen for genitive, det for dative, ben for benefactive.
Right, and directional routing cases, which are incredibly useful for a topology language. You have able for ablative, meaning from, all for allative, meaning to, lock for location or at, ill for illative, meaning into, and ella for elative, meaning out of.
Plus, instrument and discourse cases, ins for the instrument used, cause for causation, perp for purpose, and sim for similarity. So many cases.
It's a very comprehensive atlas.
Okay, but let's dissect the AST implications of this, because as a programmer, I'm used to just naming a variable destination file or user input. Taking the time to assign a formal illative or benefactive case to a payload feels like heavy academic overhead.
It definitely looks like more work up front.
Yeah. So why is this superior to just structuring a JSON object with clear keys like destination node and origin node? How does tagging something illative actually change how the compiler builds the intermediate representation?
Well, think about it like this. When you use arbitrary keys like destination node, the relationship between that data and the execution flow exists purely in the human developer's mind, or maybe in a separate schema file somewhere.
True.
The compiler just sees arbitrary strings it needs to pass from function A to function B. But when you use the case atlas, you are performing role packing at the lowest semantic level. If you tag a payload with the ill case, the illative case, the Gnot compiler inherently wires that data node to the terminal routing execution graph.
Oh, wow.
It knows natively that this data represents the internal volume a process is moving into.
So it's elevating variable relationships from just a developer convention to an undeniable compiler truth.
Precisely. And this enables automatic normalization. The documentation specifies that while you are writing the code, these cases can be completely unordered.
Oh, really?
Yeah, you can list the benefactive case before the ergative case in your script.
Hmm.
But during compilation, The gnarly parser normalizes these unordered source cases into a strict canonical key order in the IR.
So it sorts the data's topological relationships perfectly, every single time, regardless of how messy the developer typed it out.
Yes, and this creates a universally unambiguous machine-readable standard across entirely disparate applications. If application A yields a payload using standard case atlas tags, application B can ingest it and instantly understand the physical and temporal geometry of that data without needing to parse some custom schema or guess what target data to actually means.
It's essentially a universal grammar for data movement. That's brilliant. And they enforce this strictness through exhaustive pattern matching too, right?
Yes, very strictly.
Like, you cannot write a flow that ignores potential failure states.
Yeah.
If a stanza yields a tagged result, say, an OK or an error, the compiler forces you to handle both branches.
It also enforces exact arity matching for tuples. So if a tuple expects 3 values and you only unpack 2, the compiler halts.
It just refuses.
Yep. If you destructure a record, the keys must match exactly. If a required field is unmatched, it's a compile error. Now, you can use the wildcard underscore to explicitly discard a component, but you cannot implicitly ignore it. There is zero tolerance for undefined data bleeding into the runtime.
Okay, so we've established how Gnot ensures perfectly deterministic logic through the Sveckian canon, how it handles temporal state natively without mutation, and normalizes data payloads using linguistic cases. It's a huge amount of control.
It really is.
But writing beautiful, mathematically provable logic is only half the battle of software engineering. At some point, this code has to hit bare metal. It eventually needs to be deployed, scaled, and interact with the real world.
And in the vast majority of ecosystems, deployment infrastructure is an entirely separate paradigm from the application logic.
Oh, absolutely.
You'll write your app in one language,
There you
and
go.
then you write your deployment manifests in Docker or Kubernetes or Terraform. Gnot abolishes this separation entirely.
Which is huge. It weaves infrastructure directly into the compiler through the deploy and stack manifests. Let's start with the deploy contract. This is a typed manifest block inside the script that compiles into deployment metadata. And the compile time validations it runs are specifically designed to eliminate the most common causes of production outages.
Right. I mean, consider how many severe outages are caused by environment variable misconfigurations.
Too many to count.
An API key is missing, or a database URL is accidentally overwritten by an optional staging flag.
It happens constantly. A silent failure during deployment that only surfaces when actual user traffic hits the missing route and everything crashes.
Gnot prevents this physically. The deploy contract requires explicit string definitions for deploy.app and deploy.runtime. But more importantly, it forces a strict non-overlapping separation between nv.required and nv.optional lists.
Meaning if you accidentally list database URL in both the required and optional arrays, the compiler catches the overlap and just refuses to build the application.
Correct. It resolves that ambiguity before the code ever leaves the developer's machine. It even includes an optional health.smoke target natively.
Yeah.
You define your operational smoke tests right alongside your routing logic, and the compiler validates the schema of those tests.
And the compiler also takes complete deterministic control over file resolution for the build context, right? It uses very specific ignore precedents.
Yeah, it's very intentional.
It checks .notignore first. If it doesn't find a rule there, it falls back to .dockerignore, and then finally to .newtignore.
First match wins. It respects the existing tooling ecosystem, but ensures not always has the final override authority.
That's smart. And the build transforms that happen during not build are heavily automated, like a markdown file AMD is deterministically transformed into static HTML.
Yes. And TSX files are handled natively in 2 modes, depending on the manifest configuration. Either purely statically generated as server-side rendered assets, or built as SSR with an accompanying hydration bundle for client-side interactivity. All other binary assets like images, CSS, video are handled as pure byte-for-byte pass-throughs.
So that's the deploy contract handling a single isolated application. But enterprise software is rarely a single application. I mean, it's a complex web of microservices, front ends, databases, message queues. How does Gnot orchestrate multiple dependent systems?
Through the stack contract. The stack block is a typed orchestration manifest specifically designed for multi-app dependency and promotion topology.
It maps out how the different applications relate to each other. So stack.name and stack.apps are required fields. But let's talk about the dependency resolution, because I feel like this is where Gnot really flexes its computational muscles.
Oh, absolutely.
If app A lists app B as a dependency, app B absolutely must exist within the stack.apps list, but it goes much further than basic list checking, doesn't it?
It calculates the entire topological graph of your infrastructure during the compile phase.
It builds a directed acyclic graph, a DAG, of your entire server architecture.
Exactly. And
Yeah.
because it computes this DAG at compile time, it can completely outlaw dependency cycles.
Right, a circular dependency.
Right.
Where app A requires app B to boot, but app B requires app A to boot. In traditional orchestration systems like Kubernetes, you might not catch a circular dependency until you actually apply the manifest to the cluster, at which point the pods just deadlock and the deployment hangs indefinitely.
And everyone's scrambling to fix it. But Gnot makes that scenario impossible. If the compiler detects a cycle in the DAG, it fails the build. It refuses to generate the IR for a mathematically impossible infrastructure state.
It's like having a ruthlessly pedantic construction foreman reviewing your blueprints. You hand them the plans and they say, you've scheduled the construction of the roof to rely on the foundation being finished, but the foundation relies on the roof. This violates the laws of physics. Denied.
That's a great analogy. Furthermore, if you define a promotion map in the stack contract, detailing how code moves from a testing environment to staging and then to production, the compiler verifies that every single app listed in the manifest is accounted for in that promotion map exactly once.
Exactly once.
You cannot accidentally leave a microservice stranded in staging while the rest of the stack goes to production.
It forces absolute topological cohesion. Okay, I just need to take a step back and look at the sheer scale of what this compiler is doing.
It's a lot.
We have a lexer stripping away plain English poetic aliases and normalizing linguistic cases from Basque and Russian. We have an AST parser enforcing a rigid 11-step chronological sequence and validating temporal cursors that reference historical memory states. We have a topology engine calculating multi-app directed acyclic graphs to prevent circular infrastructure dependencies, and we have a build engine generating SSR hydration bundles.
It is a phenomenal amount of computational overhead.
Right, which logically implies that compiling a Gnot script should be an agonizingly slow process. If I'm doing all this mathematical proofing and DAG calculation, I should be waiting minutes for a build to finish. But the benchmarks in the documentation tell a completely different story.
The speed is where the underlying architecture truly proves itself.
Yeah, but before we hit the exact numbers, we need to factor in the primitives Gnot supports, because these add even more complexity to the compilation. Gnot includes first-class primitive call routes built natively into the language.
Yes. For handling structured payloads, you have native lanes like JSON for deterministic encoding, decoding, and projection.
What?
You have Markdown for document transforms and native table ingest for CSV and TSV formats.
But the cryptographic primitives are what really stand out to me. It has bitwise for low-level hashing and incredibly advanced capability surfaces built right in, like auth.ucan for user-controlled authorization networks, and auth.ck for zero-knowledge proofs.
Which means the compiler is fully equipped to validate cryptographic proofs natively as part of its deterministic execution.
It also exposes raw runtime telemetry through the atop module, and this is vital for the topology routing we discussed. The documentation lists telemetry endpoints like atop.entropy x, atop.freshness x, atop.confidence x, and atop.deficit x.
In a standard language, if a load balancer needs to route traffic based on node latency or data freshness, it usually has to ping an external monitoring service, mutate its own state based on the response, and then execute the routing logic.
Which introduces non-determinism and massive latency.
Exactly. But because Gnot natively tracks temporal state and memory boundaries, it exposes these metrics natively via atop. A script can mathematically evaluate atop.freshness to see exactly how recently a specific payload was admitted to the current cursor. It can use atop.confidence to evaluate the mathematical weight of a zero-knowledge proof.
It can execute complex, mathematically weighted routing decisions instantly without ever mutating external state. It just reads the raw physics of the system. Okay, so with all of this theoretical complexity, the case atlas, the DEGDs, the zero-knowledge proofs, let's look at the benchmarks, because this is mind-blowing. These were run on a standard Apple M1 processor. The baseline test was a script called apps.hello-world.gnot.
It's a fundamental application lane test, and the throughput is over 23,000 compiles per second.
23,000 complete compilations of the script every single second.
To be exact, 23,439.93 compiles per second. The mean compile time is 0.04 milliseconds. And the P99 tail latency, which measures the absolute worst-case scenarios, the slowest 1% of the execution runs peaks at just 0.138 milliseconds.
It's operating at the microsecond level. And even when they tested a vastly more complex script, one they call Paragon Feb-Delta-Som.jot, which the documentation notes utilizes complex recursion and rich mathematical helpers. The mean compile time was 0.35 milliseconds. It stays well under a single millisecond. The throughput is still over 2,800 compiles a second.
It's incredibly fast.
So we have to ask the critical mechanism question, how? We just spent this whole deep dive talking about writing code as poetry, managing linguistic cases, and building complex deployment topologies. How on earth is this thing compiling 23,000 times a second? What is the actual mechanism enabling this blistering speed?
The secret lies in the Rust-based metadata parser, known as .gnarly, and how it executes the lean style split we discussed at the very beginning. Gnot achieves this speed because it heavily leverages Rust's zero-cost abstractions and memory safety features.
Let's break that down. How does the .gnarly parser physically process the code so fast?
When you write a script full of poetic aliases, words like weave, hush, and learn test, Gnarly does not build an abstract syntax tree containing those words. It performs a single, incredibly optimized normalization pass at the token stream level. It reads the source code into memory, and using highly efficient pattern matching, it maps every alias, every unordered linguistic case, and every timeline qualifier directly into canonical kernel operators.
So it never even allocates memory for the poetry.
Exactly. The poetry is instantly vaporized. What is fed into the actual semantic evaluation engine is a perfectly minimal, mathematically uniform, intermediate representation. The engine doesn't have to spend a single CPU cycle wondering if weave means something different than fold, or trying to figure out if an illative case was listed before or after an ergative case.
Because the IR has already sorted all cases into a canonical key order, mapped all verbs to kernel intents, and verified that 11-step geometry, the execution engine is just crunching pure, unambiguous math.
Yes. And because Rust guarantees memory safety without a garbage collector, the compiler can generate these intermediate representations, calculate the directed acyclic graphs for the stack manifest, and validate the temporal cursors without pausing to clean up memory allocations.
It is the absolute pinnacle of human readability married to brutal machine efficiency. I mean, you are granting the human developer the linguistic freedom to write beautiful, expressive, case-rich poetry, but you are physically preventing the machine from ever having to execute that poetry. It only ever executes the mathematically flawless essence derived from it.
It proves that the historic trade-off in language design is a false dichotomy. You do not have to sacrifice strict deterministic logic to achieve an ergonomic, expressive authoring edge. You just have to build a much smarter parser.
It's just a phenomenal piece of engineering. We've covered a massive amount of architectural ground today. Let's synthesize exactly how Gnot fundamentally restructures the relationship between the developer and the machine.
We started by analyzing the core architectural paradox, the lean style split. Gnot provides a beautiful poetry profile at the authoring edge, allowing aliases like dual, chorus, and make, while enforcing the absolute rule that this sugar is purely visual metadata, stripped instantly during compilation to reveal a minimal deterministic kernel.
Right, and then we explored the rigid counterweight to that linguistic freedom, the Spaxian canon. By forcing developers into an unyielding 11-step sequence, who, what, from, to, where, why, with, via, by, when, during the compiler, eliminates AST geometry ambiguity. It establishes mathematically perfect replay-safe guardrails, guaranteeing that terminal clauses are always conditionally guarded.
From there, we examined Gnot's native mastery of time. We saw how it uses temporal cursors like tilde and tilde n to traverse an append-only, fully deterministic state ledger. And we discuss how it safely isolates necessary non-determinism inside quantum lanes, requiring explicit seeds to ensure historical mathematical replayability.
Then we unpacked the cross-linguistic case atlas, discovering how mapping payloads to specific roles like illative or benefactive normalizes data relationships at the compiler level. It replaces fragile human naming conventions with a universally machine-stable semantic topology.
We then elevated that logic to the physical infrastructure layer. We saw how the deploy and stack contracts calculate directed acyclic graphs natively during compilation to physically prevent circular dependencies and environment variable overlap before the code ever reaches a server.
And finally, we looked at the sheer physics of the .gnarly Rust parser, which utilizes single-pass token normalization and zero-cost memory abstractions to process all of this dense topological and cryptographic logic at an astounding 23,000 compiles per second.
It is a language that forces us to completely reevaluate the boundaries of compiler constraints and operational deterministic safety.
Which leaves me with the final thought to ponder. We've spent this entire deep dive looking at Gnot as a tool for building resilient web architecture and server deployments. But if a machine can now perfectly translate the fluid, poetic nuances of human language into mathematically flawless, deterministic execution, what happens when we start using languages like Gnot not just to program apps, but to draft our real-world legal contracts, our laws, or our treaties? If the code is poetry and the code is law, what does that make the programmer?
They become the architects of absolute, irrefutable consensus.
A fascinating and slightly terrifying paradigm shift. We are moving from a world where we argue over the interpretation of language to a world where language perfectly compiles itself into undeniable truth. Thank you for joining us on this deep dive into the architecture of tomorrow. Keep questioning the systems you build.